G'day all, how's it going? As you will have seen in the announcement, I couldn't be here live for this lecture week 8. So we're going to do 2 video lectures, one on physics and one on instructional models, ways to think about planning, learning and teaching. So as I've probably also said, physics is back on my safe ground. We've just spent a couple of weeks on biology. Which I think hopefully I've done an adequate job of, but those of you who are experts in biology could probably give me some pointers as well. Physics I feel a little bit stronger on. I had a chemistry major and a physics minor in my undergrad, but then all the schools that I taught at wanted me to teach physics. So I've probably taught more physics than chem. I've taught some chemistry. Really enjoyed teaching physics and ended up going back and completing a graduate certificate in science in the area of physics. From up to about 2012, and then started a master's in physics when I came to Griffith, but then ended up just getting too busy and had to abandon it. So it's probably my strongest discipline. I'll try and hopefully help it and weave it through, make it as clear as I can. Anyway, that's probably more autobiography than you really needed, but let's chat a little bit about physics. So we'll do the same thing that we've done with most of the others of these subject areas and look what the junior secondary curriculum says. So the Australian Curriculum Science, Year 7, change to an object's motion is caused by unbalanced forces, including Earth's gravitational attraction, acting on the object. So forces of all kinds, a rocket motor, a motorcycle engine, a rubber band, a spring, but gravity is one of the forces that we deal with a lot, obviously. So changes in an object's motion caused by forces. So Newton's laws are going to be relevant, and we'll get to those in a second. Year 8, energy appears in different forms, including kinetic energy, energy of movement, heat energy, potential energy. That includes chemical potential energy, gravitational potential energy, spring potential energy at least. And energy and transformations and transfers cause change within systems. So energy travels around through the system. Now in biology, in week 6, I think, we talked about how energy travels from the sun to the plants, to the animals, through that system. So that's one way that energy transfers. But similarly, energy travels from the sun to the plants, to the fossil fuels, into the oil, into the car, as motion in the car, as heat in the brakes, etc. So energy travels through multiple different systems and causes changes. Energy transfer through different mediums can be used using wave and particle models. So this is reasonably sophisticated for Year 9, because this is essentially quantum. It's essentially saying that light in particular has both a wave and a particle nature. We're not only talking about light energy and other electromagnetic forms of energy, we're talking about all energy, or a lot of energy can be talked about in terms of motion of waves or motion of particles. So that includes not just photons, light particles, but the particles in a mass. So as something heats up, energy transfers in, it heats up, the particles vibrate more. So the motion of the particles is part of what's conveying the energy around the place. Year 10, energy conservation in a system can be explained by describing energies and transformations. That is, energy is not created or destroyed. It is just travels from one place to another. And we can talk about the transformation of, for example, electrical energy in a circuit into light energy in a light globe, into heat energy in the atmosphere, and so on. And motion of objects can be described and predicted using laws of physics. Remember that I talked about laws of science having descriptive, so the ability to describe, predictive, the ability to predict, but also the ability to explain, explanatory power. So they haven't put that in the syllabus here because they don't understand science as well as me. No, I'm joking. But that's what we'll be talking about, is how do these laws of physics explain motion? How do they give us causal relationships that explain motion? So that's what the syllabus document, the Australian curriculum, says. And this week we're going to talk about motion, the motion bit, and the other next week about the energy bit. Because if you actually looked at those 4 years and the multiple statements, effectively there were some statements about motion and some statements about energy. When we talk about energy and particle motion, the two are related. So the two, like almost all of these distinctions, it's kind of artificial. We're chopping the world up into manageable parts for us to understand. But the world, everything is interactive and dynamic. So let's see how we go. language is really important, the literacy of science. So not scientific literacy. Scientific literacy is an interesting concept. It's used quite a lot, but it seems to mean something like understanding enough science to get by in the world. So being a literate person in the English language sense, or the whatever your language sense. I went to a conference presentation the other day by a Swedish guy, and he was talking about in class in Swedish, and of course that's the equivalent of English in that country. That's the learning your own language, and thereby learning language as a thing, of course, that they have. So anyway, that's a major digression. We talk about scientific literacy as knowing enough literacy to get by, just like being literate is knowing enough language to get by, to be able to read a street sign, to be able to fill out a form, to be able to just do the things you need to do to be able to live. And then you can have a higher level of literacy as well. Scientific literacy, enough to be able to vote, enough to be able to not be ripped off by charlatans trying to sell you nonsense. But then obviously there are higher levels of scientific literacy. But what we're talking about here is the literacies of science, or the literacy of science, which is the way language is used in science differently from everyday language. So there are terms like speed that's used in everyday language, and I don't mean the drug ice. I mean how fast something is going. Speed is just, let's think about speed differently. You see on the billboard, you'll get a speeding fine, etc. But speed has a particular technical definition in science that we'll talk about in a bit. The word theory, if you've read the reading that I posted about facts, theories, and laws, you know that theory means something quite different in science from what it means in everyday language. So the ability to use language in these specialized and technical ways that science uses it, rather than in the general and everyday way when we're talking in science. We have to obviously be able to do both, have both in our repertoire, but when we're doing science, we use the language the way science does, if that makes sense. And it's part of what we do as science teachers, is develop these conventions of communication, these skills in using particular language. So scalar and vector quantities are two different kinds of quantities. A scalar just has a size. So something like a dozen eggs is a scalar. We say that we have 12 eggs. We don't say, or 1 dozen, we don't say that we have 12 eggs northwest. Right? Adding a direction onto that kind of number doesn't make any sense. So you can see here, in science, we use the notion of mass as a scalar. So if something weighs 1 kilogram, again, it doesn't weigh 1 kilogram upward or downward or sideways or northeast. It weighs 1 kilogram. That's a scalar number. It will have a force acting on it downward due to gravity, and the force is a vector. The mass is a scalar quantity. So you can see those examples. So distance is a scalar. If I went out and walked around campus, I would go a little bit this way, a little bit that way, a little bit up and down and around and whatever. I could say, my app would tell me that I've walked 3.4 kilometers today. But I might be back where I started, or I might be 100 meters from where I started, but I've walked 3.4 kilometers. So that's the distance that I traveled. I don't care about the direction, it's just distance covered. That's distance, that's a scalar quantity. But if I do care about where I am relative to where I started, so my displacement from the place I started, then I can measure that. I can say I am 100 meters from my starting point, and I'm north of my starting point. So the distance, my displacement, would be given as 100 meters north. My distance would be given as 3.7 kilometers, because that's how far I've actually traveled. But displacement is the final, the difference between the final and the initial, and it's a vector quantity. It has a direction related to it. So speed, if I go for a ride up through the hills, up the twisties up the front of Beachmont, I can have an average speed of 60 or 80 or whatever it happens to be up through there. For want of legal purposes, 60. But in fact, I'm changing direction all the time. So even if the speed stays the same, a change of direction means a change of velocity, because velocity is the vector quantity, which means the direction counts. So say that I'm going forward at 60, and then I turn 90 degrees left, and now I'm going 90 degrees left at 60. I have the same speed, the same scalar quantity, the same number, but I have a different velocity because I'm going a different direction. So direction's important in velocity. Acceleration is, again, a vector quantity. You accelerate in a particular direction. A force, obviously, acts in a particular direction. And momentum, which we'll talk about in a bit, acts in a particular direction as well. So these quantities are really helpful because a vector, if you want to add up some displacements or velocities, you have to do some particular maths to make the vectors work. Now, this is probably a little bit beyond junior secondary. It's going into senior secondary, but this is quite early year 11 senior secondary stuff. And it's useful for you to know where they're headed. So let's keep on cruising with that. So Newton's laws of motion. People just say Newton's laws, but Newton also had laws of heating and cooling and various other things. So it's better to say Newton's laws of motion. These are the specific ones. And these are my wording of them. Different people use different wording. I've tried to write the wording over the years, and I've refined it over the years to one that I think is clearest for students and makes the most sense to students. So the first law, objects will remain at rest or in constant velocity motion unless acted on by an unbalanced force. So what do we mean? We mean that objects will stay still or else they'll stay moving at the same speed in a straight line. So constant velocity is a technical term because remember, velocity cares about direction. So to be in constant velocity motion, they have to move at the same speed in the same direction. And what this law is saying is that unless a force acts on something, it will stay how it is, either at rest or in motion in a straight line. Now, those of you who have some physics background will understand that those two things can't really be distinguished because motion is relative. One motion relates to another motion, and there's no absolute standard of what's moving and what's still. So if I'm standing here in the studio, I feel like I'm standing still, but of course the Earth is spinning. I'm not all that far from the equator. I might be doing 1,000 kilometers an hour on the Earth's spin because I've got to get around the whole world in a day. So being able to detect when we're moving and when we're still is kind of a whole other argument. That might be, again, tweaking your melon, bending your brain a little bit at this point. So let's leave that on the side of our plate. But stay at rest, so things will be stopped, or else they'll keep moving in a straight line unless a force acts on them. Now, go back to the example of pushing a trolley across, a shopping trolley across the car park. If you push it, you're putting a force on it. So it was originally at rest. You put a force on it, it goes forward at a particular velocity, and then it does slow down. But hang on, what's going on there? There's friction. There is bumpiness on the surface. There is friction in the bearings of the wheels. So there are forces acting in the opposite direction to the motion, and those forces cause it to slow down and stop and return to rest. We'll talk about those in the other laws. But without any force acting, so say you had a shopping trolley out in space, out where the Voyager spacecraft is further out than Pluto now, and you pushed it out there, because it's out in space, there's no atmosphere, there's nothing to hit it, nothing to slow it down, no frictional forces, it would keep going in a straight line forever, because there's no forces acting on it, until it ran into another star or got into a gravity well of another star, or until the one hydrogen atom per cubic meter out in interstellar space impacted on the front and slowed it down over thousands, millions of years. But with no forces acting on it, it would keep going in a straight line at the same speed forever. Okay, so that's Newton's first law of motion. Second law, the acceleration of an object is directly proportional to the force acting on it and inversely proportional to its mass. Now, that's some big language, but it actually makes perfect sense. If I'm pushing something, I want to make it accelerate. It's currently at rest and I want to make it move. The most common time I push something is a car with a flat battery. So if I'm pushing a car with a flat battery, I have to make it accelerate up to a speed where I can jump start it. And if the car is heavier, if its mass is greater, the acceleration will be smaller. If I push with the same amount of force, but it's a massive truck instead of a Kia Rio or some tiny little car, then obviously the acceleration will be less for the same force. Does that make sense? So that's what inversely proportional means. As the mass gets bigger, the acceleration gets smaller. For force, it's the other way around. if I push on the Kia Rio, but then my buddy pushes beside me and my other buddy who's a rugby league front rower pushes beside him, we've got a lot more force, same mass, the acceleration's bigger. So it's directly proportional to the force. Bigger force, bigger acceleration. That's what directly proportional means. Inversely proportional, bigger mass, smaller acceleration. So hopefully that's clear what's going on. This is often written as F equals ma, but I've written it as A equals F over m because that directly corresponds to the words. Acceleration is directly proportional to the force on the top line of the equation, and it's inversely proportional to the mass on the bottom line of the equation. So in other words, if the bottom line of the equation gets bigger, it's a fraction, the whole thing will get smaller. Right? If the bottom line of a fraction is bigger, the fraction itself is smaller overall. So hopefully, again, that's clear. So that's the second law of motion. Third law, for every force, there is a force of the same magnitude. Magnitude is just a big word for size. If there's a force of the same size in the opposite direction that acts on a different object. Now, this one is often stated as, for every action, there's an equal and opposite reaction. That's the usual language people use, but it's very, very imprecise because it doesn't specify force. Action could be anything. It's not a technical term in physics. And it doesn't specify where the force acts and so on. So it's much better to say, all right, so if I grab my, this is going to mess the video up, if I grab my Coke bottle and sit it on the desk, which you can't see there, but you can tell the desk because otherwise I'm magically holding it up. And let's pop it, that way. I'm having a Coke with Megan today, apparently. Then I'm not exerting much force on it with my fingertip there. I'm just holding it in place so it won't fall over. The desk is slopey. But the bottle is exerting a force downward on the desk. The desk is exerting a force upward on the bottle. Those are the same size, same magnitude. The force exerted downward by the bottle on the desk and the force exerted upward on the bottle by the desk are the same size. They act on different objects. One acts on the desk, one acts on the bottle. And because they are the same size and because they act in opposite directions, the bottle is not accelerating. So that actually applies back to the first law. There's no unbalanced force. There's only a balanced force here. There's a force acting upward on the bottle. There's also a force acting downward on the bottle from gravity. And the bottle is exerting a force upward on the earth from gravity, which we'll talk about in a sec. But overall, there's no unbalanced forces, so there's no acceleration happening between the bottle and the earth. Okay, I'm going to get the bottle to stay there. All right, so those are Newton's laws. There are some equations where we can do some calculations. They are probably a little bit beyond our topic, and given that I think the time is ticking by, we might actually even just leave that on the side of our plate. But very quickly, final velocity equals initial velocity plus acceleration times time. Distance equals initial velocity times time plus a half acceleration times time squared. Probably more than we really need. So, and I'm aware that some people will be quite uncomfortable with these, even as comfortable junior secondary science teachers. So they basically are ways that we can calculate something's, the time it will take to accelerate from a slower to a faster speed or vice versa, or the time it will take for various things to change, the distance that will be covered and so on. But as I say, beyond our scope really. In the lab, we are going to play with pendulums. Pendulums are a lot of fun, and we're going to determine the value of g, the acceleration due to gravity, using our pendulum. We're going to rearrange that formula to make g the subject. If you're feeling really brave, you can test out your algebraic skills and do that yourself, but I will walk you through it when we get there. And we will conduct an experiment to determine what the value of g is. It's an interesting one because we already kind of know. You probably can remember from school that 9.81 meters per second squared is the acceleration due to gravity near the Earth's surface. So we kind of already know the answer. We're trying to figure out how accurate our experiment is toward that answer. So I'll leave that on the side of the plate as well for a minute. And that's the last slide, but I did think I mentioned that I was going to mention something. What was I going to mention? Doesn't matter. Forgot a bit. Okay. All right. That's our very, very brief introduction to motion. The key concepts really are about those different languages, about the difference between displacement and distance, the difference between velocity and speed, the idea of acceleration, the idea of mass, and the fact that mass is what makes it difficult to accelerate. If you've got something light, it's easy to accelerate. If you've got something with a heavier mass, it's harder to accelerate. I guess the other thing I should mention is that weight is the name given to the force that gravity exerts on a mass. So we use this interchangeably as well. It's another one of those languages that we use carelessly often. But basically, my bodily mass at the moment is about 93 kilos, something like that. I have been as small as 80 in the last 5 years or so. I'm trying to lose a bit more now. This is probably not information you particularly need, but that's a mass. It's measured in kilograms. A weight is a force measured in newtons. So the weight force on my body on Earth is that 93 kilograms times the acceleration due to gravity, 9.8. So 9.8 is close enough to 10. It's about 930 newtons of force pushing me down on Earth. Now on the moon, because the moon's much smaller, has much less gravity, as you saw from the moon landing videos, my mass would be the same. I would still be 93 kilos. I would still have the same muscle and fat and bone, but my weight would be smaller because gravity would exert a smaller force on me. It would be only about 1/6 as much. So it might only be 150 or 200 newtons instead of 930 newtons. So the distinction between a mass, which is a scalar quantity, and a weight, which is a force, a vector quantity measured in newtons. I guess the other thing is I haven't mentioned units very much. So fortunately, we're very lucky. We live in a country that uses metric, uses SI, the System International, the very sane and very French system of everything being multiplied by 10. Some of us are old enough to remember feet and inches and yards and pounds and stone and all of those other very strange things with 12s and 14s and 16s and other awkward numbers in them. But our units really are pretty simple and pretty clear in science, in English-speaking countries generally, almost every country except the United States, and to some very small extent, England for some reason, or the UK, I guess, they still talk about miles rather than kilometres, but almost everything else is metric. So anyway, that's probably way more than you needed for right now. I hope it's helpful, and I hope it's not shell-shocking, but I hope it gives you a sense of the physical world around us, and again, how our theories help to explain our experience, describe, predict, and explain.